This is the final lesson on our introduction to maximum, minimum, and points of inflection. We're going to talk a little bit about increasing and decreasing functions as well. Okay, increasing and decreasing functions, well, we should have a pretty good idea of what that means just from our common sense, our intuition. But more specifically, as x increases, f of x increases, that's an increasing function. If f prime of x is greater than 0 on an interval from a to b, then f of x is said to be continuous on that interval. So we have some functions here. We have, in red here, we've got y equals x minus 1, and this is a strictly increasing function. For every x, f of x is a little bit bigger than it was before, so it's increasing. Here we've got y equals x cubed, and it's actually a little bit debatable whether this is increasing on its entire domain, because there's a point here where f prime of x is equal to 0. And so I think most people would say this is increasing on its domain. It's just not a strictly increasing function. And then if we talk about decreasing, we can use the same language for decreasing. If f prime of x is less than 0, then we have a decreasing function. And we actually use these terms more in general in intervals. So for example, for y equals x squared minus 2, here we would say the function is decreasing for values of x less than 0, and for values of x greater than 0, we would say the function is increasing. So we talk about the intervals of functions rather than talking about the whole function itself as increasing and decreasing. That seems to be a little bit more valuable. At any rate, another idea that we need to talk about is concavity. And so concave, like cave, if it's facing downwards, we say these are all examples of concave down portions of our graph. Portions of our graph that look like this are described as concave up. A point of inflection is where the graph of our function changes concavity in either direction, from concave down to concave up or vice versa. The way we find this algebraically is we would find the second derivative of our function, set that equal to 0. The point that we get could be a point of inflection. What we'd have to do to be certain is we would have to check on either side of that point to see if f double prime changes sign. So if f double prime changes from positive to negative or negative to positive at that point, then it is a point of inflection. Now in our course, pretty much f double prime, if it's equal to 0, it's pretty much always going to be a point of inflection. We won't give you some sort of funky function where that is not the case. So this leads me to a word of caution. In our course, we make a lot of assumptions that make our study of calculus a lot easier. But if we really wanted to be critical and really wanted to be precise, then we would have to pay attention to far more details. We could get really bogged down in the details, and that's the reason why our course has made these decisions to study functions that behave very nicely, so that we can have a much general sense of what's going on with our calculus without getting too bogged down in the details. So at any rate, let's try to put all of this together. And so rather than use this slide here, I'm going to go ahead and use the this concoction that I've made. Now it's very busy here. I've got a few different functions. Here's the f of x here in blue, and it's a cubic. And the first derivative of this function is here in red, and then the second derivative is this line in black. So I wanted to put them all on one graph so that we can take a look at them and put all these concepts together. So I have a point on our function here, and you notice in light green here is the slope, is the tangent line through this point on, and as we move across, as we see that A is increasing, and although A is increasing, the slope of the tangent line is decreasing, and it gets smaller and smaller and smaller until eventually we get to 0 here. And we can see this with this red portion of our graph. So our function's increasing, it's concave downwards. So what that results in is our derivative is positive, but it's getting smaller and smaller and smaller until it gets to 0. And then it changes from being positive to negative, right? And the slope of our tangent line goes from positive to 0 to negative. And now it's negative as x is increasing. Our slope is getting increasingly negative. All right, it's getting more and more and more negative until we get to this point. And so we can see this with our graph here. The value of our slope is getting more and more negative all the way until we get to this point here. And we can see that our tangent line doesn't get any more negative. It's still negative. The slope of our tangent line is still negative, but it's becoming less negative from that point, less and less negative. And in fact, it's getting almost until it gets here where it gets to 0. Okay, and again, if we look at our graph here, the slope, the value of our slope is actually negative, right? Right about here is about -2. So it's negative, but it's getting less and less negative all the way until here. And then we can see that the slope of the tangent line is positive. It goes from negative to 0 to positive here. And so we see this here. The value of our slope becomes positive and then increasingly positive. It gets more and more and more positive as we come through here. Okay, now let's take a look at that point of inflection, which happened right back here. So what happened was the slope of our tangent line became more and more and more negative until it got right about here, where it reached sort of its maximum negativity, and then it became less and less negative until it came over here. So the point of inflection is the point where the concavity changed. It was our slope was getting smaller, 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 all the way through here. Right? It was positive, but it was smaller, 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 0, smaller, 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 until I get all the way over here. And then at this point, it starts getting bigger, 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 all the way through here. So our point of inflection shows us where we change concavity from concave down to concave up. So we would say our function is concave down, up from negative infinity all the way to positive x equals positive 1/2, and then is concave up from x is equal to positive 1/2 to positive infinity. We would say our function, our blue function here, is increasing from negative infinity all the way to -1, and then is decreasing from -1 all the way down to 2, and then is increasing from 2 off into positive infinity. So to use all of our vocabulary terms and all of our mathematics and algebra, if you understand this picture, completely, then you understand what you need to know from this section.